Nuclear Delivery Systems Part 2. What's odd about this picture? Well, if you look closely at it, you'll see that in the northeast US, there's a huge blackout. This occurred in 2003. This is just to illustrate how fragile our electrical grid is. And a nuclear war would wreak enormous havoc. Aside from the direct destruction of coal and hydropower and electrical stations, you'd have enormous damage to the infrastructure and you'd have fallout everywhere, so you wouldn't have the immediate response of crews repairing the infrastructure. An important measure for missiles is their circular error probability, their CEP. It's a circle with a radius within which 50% of missiles will fall, measured in meters. An alternate method used by the Soviets is the maximum error, the ME, and it's 2.3 times the distance of a CEP. It represents the zone within which a missile will land 99% of the time. Doubling the accuracy of a missile or a delivery system of a nuclear warhead permits an 8-fold reduction in megatonnage for the same effect in overcoming the overpressure resistance of a silo or a bunker. So it tells us accuracy is far more important when hitting counterforce targets, meaning military targets, when you're using missiles in an attack. So accuracy has become so great with highly accurate missiles that PSI has almost become irrelevant because the crater created by the detonation would make launching impossible. It would basically shift the silo. It would put it on its side. So mobile missiles were sought by countries like the Soviet Union and Russia and China today because they could take the missiles out of the silo and put them on submarines at sea, but Chinese submarines in particular and Russian submarines today less so are louder than American submarines. They can be tracked and followed. And because of that sense of vulnerability, the Chinese and the Russians prefer to keep their missiles on land, although the Russians do have a fairly strong ballistic missile submarine force. So, for example, the LGM-118 Peacekeeper missile, the one I identified earlier as sort of the journalistic MX missile, has a circular error probability of 100 meters. So that means 50% of the time it'll land within a football field of a target, with the actual missile at the end of the football field. So it's actually a radius of 100 meters. And 50% of the time, for a variety of mechanical or weather reasons, it'll land outside of that area, although we don't know how far outside of that area. Missiles have been getting considerably more accurate over time and now average around 300 meters, 3 football fields, after flying 10,000 kilometers. That's actually a distance that's greater than you have to fly over the Arctic Circle between the Soviet Union and the US. Because the shock wave from a nuclear weapon dissipates quickly, highly accurate weapons are needed to destroy modern silos, even warheads in the megaton range. Here you can see a graphic. From the top to bottom, you've got a small warhead that's very accurate, and so it touches the silo, so it damages it. And it has the same effect as that much bigger detonation below. And the very bottom one, the very bottom graphic, is of a missile that missed. The circular error probability wasn't very good. Here you can see different modified versions of Soviet-era rockets and their improvement over time. The SS-11 Mod 3 had an estimated circular error probability of 1,100 meters. The SS-19, which is a current Russian missile, is down to 300 meters. The SS-18 has shown remarkable improvements. It's down here to 300 meters as well, the Mod 4. This is the SS-18, the Satan, the largest ICBM in the world, which even now is still deployed. Although every year fewer are in service, according to the military balance published by the International Institute of Strategic Studies. Here you can see the remarkable increase in accuracy. Accuracy is the vertical axis in circular error probability, the meters. And you can see the year of deployment. So across time, the first Titans, Titan II there, in the early 1960s had a circular error probability of around 1,300 meters, good enough to destroy a city, not destroy a silo. And then you've got remarkable accuracy with the Minuteman II, the 3 Mark 12A, which is a bust system. And then you've got the Pershing IIs. And by 1985, you're looking at 50 circular error probability. You could put this thing in a particular building on a particular block. And the Soviets were very concerned with the Pershing II because it also had a very low trajectory, which meant it flew below the radars. And you can see the MX missile, which is the Peacekeeper missile, no longer in service. The Trident D5, which is launched out of a submarine at sea. And it's not always easy to determine where you are at sea. And plus you're rocking and rolling in the water. And yet, it can achieve this level of accuracy. In fact, the Trident D5 was in a program where American submarines could launch missiles for tactical battlefield use. So someone would call in from the battlefield. It would work its way up the chain of command very quickly, and then the submarine would launch a missile with battlefield impact. For that, you need incredible accuracy. So this brings us to the second delivery system, the SLBM, the Sea-Launched Ballistic Missile. The submarines that launch them are coded SSBN, and they're called ballistic missile submarines. SSBN is not an abbreviation. It means subsurface ballistic nuclear. And nuclear indicates not the rocket it's carrying, but the engine it's carrying. And these vessels need nuclear engines because they need to go underwater and stay there for a very long time. So they need continuous energy, where if you had an internal combustion engine, it needs oxygen. So you'd either have to generate it from the water around you or stick a snorkel up to the surface of the water, and then you'd be visible by anyone who had a radar on an airplane. The US SLBMs are typically ejected by gas pressure, and then the engine ignites as the missile breaks the surface. So you can see a sea-launched ballistic missile Poseidon tubes that are open. Obviously, they're going to get filled up with rockets. Out of curiosity, the British and Americans share shares in a publicly held company in the US which owns and refurbishes the missiles. So when the British ballistic missile submarines and the American ballistic missile submarines want to get missiles, they finish their tour of 3 months, they deposit the missiles, then they would go back for refurbishments for the submarine, and then they would go back to that company and the missiles would be put in the tube. So the British are almost completely dependent on the US for their ballistic missile submarine missiles. And a missile that was serving in a British submarine in one 3-month block could then be deployed in an American submarine in the next 3-month block. So it's a very curious sort of system where you have a private company controlling the missiles of two countries. We have a C4 Trident MERV, which is, again, multiple independently targeted reentry vehicles, which were launched on a C4 Trident, which is an earlier submarine missile. It has multiple warheads. And on top you can see a Soviet Delta I ballistic missile submarines. The Soviets had a lot of these very loud submarines all over the place. Here are the family of different American sea-launched ballistic missiles. The Americans are still using the D5. They're larger. They actually have remarkable range, and they're incredibly accurate. And they have multiple warheads that are bussed in the MERV on top of the warhead, on top of the missile. This is a comparison of some of those systems. You've got the Arahant at the bottom, which is the Indian system. You will see it in one of the simulations. The Arahant doesn't have the range to hit the interior of China. The missiles could not go farther than Tibet if they were to be used against China. And I don't think it's reliably quiet enough to be deployed in the South China Sea without being detected by the Chinese. It's more likely to be used as a symbolic second deterrent against Pakistan, although I don't think it's really going to deter Pakistan, because Pakistan, I don't think, has the counterforce ability to blow up Indian missiles anyway that are on the surface in India. The next is the Zia class, which is no longer in operation. It was China's first ballistic missile submarine. Not the first, but the first one that was operational, or was almost operational. The Triomphant is the French system. Then you've got the Jin. The Chinese have 4 of these. It's the current standard system that's deployed in the world. You've got the Vanguard. The Triomphant and the Vanguard there's 4 of each. The Triomphant is French, the Vanguard is English. You've got the Delta IIIs, which the Russians still have some of them today. The Bore is the new Russian ballistic missile submarines. You've got, I think, a 14 Ohio class. which the Americans operate. And some of them have been conventionalized to launch banks of cruise missiles and missiles for other purposes and special forces. So it's sort of a versatile system. The Americans have a lot of them. And finally, the Typhoon. The Typhoons were the biggest ballistic missile submarines in the world. They're basically double-hulled, giant titanium machines. Not the quietest, but they carried a lot of missiles. They're problematic in the sense that a lot of them were not well maintained, and they fell apart for mechanical reasons. And I think there is one or a few that are still operational in the sense that they could be sent to sea, but they're not routinely sent out on deployment. There are two different approaches to deploying submarines. The Americans, the English, and the French have very silent submarines, and these deploy individually deep into the ocean at relatively high depths because the water provides a barrier to electromagnetic detection like radar. And if you're in the deep ocean, you can avoid acoustic systems. And some of the acoustic systems are incredibly sensitive. Wang, which is a company that's now bankrupt, specialized in underwater microphones, and they could listen to fish and whales thousands of nautical miles away. I mean, it's really incredibly sensitive systems. Now, if you are not confident in the quietness and the stealthiness of your ballistic missile submarines, you normally put your submarines in Bastions. So the Soviet Union during the Cold War had two Bastions. One, which you can see in the center of the map in blue at the top, at basically the Barents Sea, which was under ice a part of the year, and the base there is Polyarny, the main base. There are many bases there. And so these submarines would base there. And if you look on the right side of the map, there's the Sea of Okhotsk, the other blue submarine, and it was protected by a ring of bases on the Kuril Islands. And the main base there was Petropavlovsk. And these two bastions would be places for the submarines to hide. Both areas of water were several kilometers deep, so the submarines could go down 300 or 400 meters, and you had a navy on top, on the surface of the water, to protect those submarines, and you had local bases with anti-submarine warfare helicopters and other submarines and aircraft that did maritime patrolling and anti-submarine warfare. And so there was a layer of protection on top of the submarines. And even if the fleets were destroyed, the surface fleets, the submarines could, in the Barents Sea, could then escape underneath the Arctic ice cap on the North Pole. And the submarines in the Sea of Okhotsk could hide under the ice that was there seasonally. These are good bastions because they're deep. Now we compare it to, say, the Hudson Bay in Canada. The Hudson Bay in Canada is got an average depth of I think 150 meters. It's very shallow. So it would be conceivable that you could design a remote system to detect the submarines hiding there. So although the Hudson Bay looks like a fantastic place to put a ballistic missile submarine, or say the Great Lakes, Lake Erie or Lake Michigan, in general they're very shallow. They're not optimal. You want depth. Now, the red submarines were patrol submarines of the Yankee-class long range, carried fewer missiles, shorter range missiles, and they were deployed on the east and west coast of the U.S. The U.S. had backscatter radars deployed until shortly after the end of the Cold War that could detect the launch of a missile against a background radar scatter of the movements of the ocean. And so the Americans would need to get early warning, because a submarine that would be that close, although the Americans did have hunter-killers, they're looking for these things all the time, and they had a sensor network called SOSUS. The Russians had a system called Caesar, which is a series of underground microphones that would listen to the submarines. And so the Americans would track these submarines, but if the Soviet submarines were to launch, they would launch rockets high into the atmosphere for an electromagnetic pulse, and then it would take them about 10 minutes to put a nuclear missile onto Washington and the Pentagon. It would take them longer to get a missile onto NORAD headquarters in Colorado, because it's in the center of the continent. But within a few minutes, perhaps 15 or 20 minutes, they could get a couple of rockets down on top of American silos and air bases in the center of the continent. So the Americans didn't have bastions. Their submarines went all over the place. Now, the issue for the Chinese today is that they have no bastion. The water, like the Bohai and East China Sea, from China to Japan, is so shallow that if you were to take an aircraft carrier and tip it up so it's vertical, the end would stick out. So Chinese submarines are incredibly visible because of the very long extent of the continental shelf. So China's been trying desperately to create a bastion in the South China Sea because the southern part of the South China Sea has the depth necessary to hide ballistic missile submarines. Unfortunately, the U.S. and the West is not cooperating because it's a violation of the UN Law of the Sea. India has the backyard of the Indian Ocean to hide their Arahant ballistic submarine. Israel has actually a Dolphin class, a Type 209 that they bought from Germany. And the Israeli underwater deterrent consists of cruise missiles, which is smaller missiles, shorter range, smaller warheads, but useful nonetheless for Israel. Pakistan, to my knowledge, does not have a ballistic missile submarine. Recently we saw North Korea launch a missile from underwater, but we're not entirely sure what the platform was that they launched it from. So here you can see different sea-launched ballistic missiles. In general, sea-launched ballistic missiles are too inaccurate to hit silos. They're too difficult to hit. So it's not your optimal system for that kind of targeting. For that you would use ICBMs. You could use perhaps cruise missiles launched from submarines, but they're not going to fly anywhere near fast enough to get there, because cruise missiles fly at the speed of an aircraft, and flying across the US is going to take you several hours. Where a ballistic missile will be exoatmospheric in space, it'll fly through the vacuum of space and pick up enormous speed, and then they come in around 7 to 11 times the speed of sound, which is incredibly fast. And necessary if you want to stop rockets from leaving their silos. Because rockets, when they come out of their silos, they're initially quite slow. So here at the bottom left, you can see a Soviet-era Typhoon ballistic missile submarine, absolutely enormous. You can see a U.S. Ohio ballistic missile submarine in, I believe, the center. In the top left, you can see a UK. Actually, that's the HMS Revenge, which is a British ballistic missile submarine. And you can see two missile launches on the right. The bottom one is the Poseidon, and the top one is the Polaris. Another way to launch missiles is intermediate range ballistic missiles. Here we have a map of Europe and European Russia, and what happened in the 1970s was the Soviets deployed a missile called the SS-20, which was basically done for intimidation. I'm not sure what the point of it was. It was a good theater missile. It could blow up air bases and targets in depth in Germany. But, the Soviets could have done that with a bigger, longer range missile. But it led the Reagan administration to deploy the Pershing II in Holland, Belgium, Sicily, and parts of the UK and Germany. Mostly the Pershing II was in Germany. And they deployed cruise missiles in Sicily, Holland, and Belgium. And these missiles were very difficult for the Soviets to intercept and stop. When I visited the Soviet Union in 1987, it was just a week after a German pilot called Rust, who's a bit of a, I would say, a daredevil or possibly a nut. He flew a Cessna-type light aircraft from Germany to impress a nurse through Soviet airspace and landed at Red Square in Moscow without being intercepted. And a whole bunch of air defense marshals in the Soviet Union were fired, marshals of the PVO, and he served some time in jail. And I arrived at Red Square, and the guide there had to sort of, a little bit humiliated by what had occurred a week earlier. This individual was a bit of a nut. He went back and was later arrested for threatening someone with a screwdriver. So the point is that the Americans had cruise missiles and Pershings that could easily get through Soviet air defense, because the cruise missile flew so low that only a downward-looking radar on a sophisticated Soviet aircraft could detect it, and then they would have to have a general idea of where it was. And the Pershing had a very flat trajectory. It didn't fly very high ballistically. It actually flattened out. So the Soviets were afraid that America could do a first strike. So the point of that was there was an era in the 1980s when you had a lot of these intermediate range ballistic missiles, and they were talked about every second day in the newspapers. Ultimately, Ronald Reagan's deployments achieved their goal, which was to pressure the Russians into negotiations to get rid of their missiles. And this led to a treaty, the INF Treaty, Intermediate Range Nuclear Forces Treaty, in which both sets of missiles were removed. Now, the way the Americans got rid of theirs was they took them to a desert under satellite inspection and dismantled them under full observation of the Soviets. Now, we think of Soviet engineering as somewhat crap. The economy sucked. The Russian people rejected the Soviet system fairly abruptly in 1991. So the Soviets took their missiles out and thought, well, you know what, let's fire them off. Let's fire off the 72 SS-20s to see how they would have worked. What do you think was their rate of success? Well, as it turns out, 100% of the 72 SS-20s the Soviets launched operated according to design. The Americans, needless to say, were shocked. The Russians did invent the periodic table, so you'd give them credit as one of the early thinkers about rocketeering, that especially some of the formula about how to launch a rocket into space and the ratio between the weight of the rocket and the sort of the derivative of the loss of the weight from the expenditure of fuel. You have to give the Russians credit for good basic science. So here are some systems. You've got a Pershing 1 missile. These were missiles that were deployed in Germany. In fact, I think this is not a Pershing 1, but it's a Pershing 2 with the colors of a Pershing 1. The Pershing 1 was a joint American-German rocket. The Pershing 2 is controlled exclusively by the Americans. You've got an SS-3 Shyster, which I believe is on the top right, an SS-4 Sandal on the bottom right, and an SS-15 Scrooge, which is the top left. Here is an Economist article showing the DPRK, the North Koreans, and a range of their different missiles, in particular the Taepodong-2, which was North Korea at that time. This is a very old slide showing the North Koreans working on their version of an ICBM and the plutonium warhead it would carry. You can tell if a country wants to build a long-range system by the type of warhead. Iran wasn't pursuing aggressively a plutonium system, so it looks like Iran's focus is local. It's trying to intimidate Saudi Arabia, Iraq, and Israel. But North Korea wants to fire a nuclear weapon at the US, and so they went for a small plutonium warhead. Now, the reason I'm showing this to you is to show you that the Earth is not flat. It's actually curved. And in the subsequent issue, there was a correction printed by the Economist to show you that this is the actual range. So, maps are flat. Countries are not flat. This is the RSA-3, which was a South African missile, which, when it went on display, caused an absolute uproar because the South Africans were building an intermediate-range ballistic missile to fire at who? Who could possibly be a target of this missile? Now, the main issue with this missile is it's actually a repainted Israeli Jericho-3. So Israel, in exchange for the uranium they got from South Africa, because South Africa and Israel were both pariah states to some extent, particularly Israel's nuclear program. Israel was not able to get uranium from the US or from any European state. So South Africa has something like 30% of the world's uranium. So the South Africans gave Israel uranium, which they then used at their Dimona site. And in exchange, Israel provided some technical skills to the South Africans. The South Africans built their own nuclear weapons, and so far we found no evidence that they needed Israeli help for that, but they did need Israeli help for the rockets. So immediately, the U.S. Tried to sanction South Africa, but South Africa was already sanctioned to the hilt, and the Zionist lobby in the U.S. basically neutralized any move by the U.S. to stop Israel. The main consequence was that the Russians were very upset because the U.S. looked like they permitted Israel to give South Africa an intermediate-range missile, and so why can't the Soviets then give other countries the same system? And the Americans didn't want the Soviets giving hostile countries very long-range missiles. Now, this missile is actually the French M620 and 660 series. Charles de Gaulle, when France's oil dependence increased, he pulled France away from its relationship with Israel, which had emerged because the French were fighting in Algeria and they wanted an ally in the region that looked like it could divert nationalist Arab attention. So when France's foreign policy shifted, Charles de Gaulle basically cut off weapons to Israel. Israel went to the U.S., but as basically a parting gift, so that there was no serious ill feeling, and probably to make some money, the French sold the M620 series to Israel. So this is a French missile, basically making a tour of the globe. This is a Japanese civilian rocket used to launch satellites, but of course this particular system is actually liquid fueled. Japan's been rapidly developing the techniques for solid fuel launches, and so clearly there's a strategic implication for these new space program vectors. This is the Saudi DF-3, which was purchased from the Saudis, from the Chinese. The Chinese, when they exported this missile, were not doing it with a view to affecting the strategy of the Middle East. The sale was made in the 1980s. The Chinese were looking for hard capital, and the Saudis had an enormous surplus of Western currency, particularly US dollars. So China sold the rockets. It caused an uproar again in the US, and Israel was rather hostile, but Saudi Arabia's main interest was to aim them at Iran, which was then engaged in a war with Iraq, the Iran-Iraq war from 1980 to 1988. The thought is that this system can have a Pakistani warhead installed on it, and then it would be an effective deterrent against Israel, which has nuclear weapons. The base is actually to the east, about 1,000 kilometers of Riyadh, the capital of Saudi Arabia. So the base, there's an operational base, and it's got some. Here you got a mobile launch system, but I'm not sure. I'm not sure if this is the main way that the Saudis launch the system. Now we come here to short-range ballistic missiles. I had a colleague of mine who well, he's an officer, David Chloe, who worked as I did as a scholar in Pakistan, but as a youthful New Zealander, he actually served in the British Army, the BAOR, the British Army on the Rhine, which is the British land army deployed near Hanover in West Germany to stop a Soviet invasion. Now, they operated the Honest John, which is the rocket that you see here on the left. And so they went out one day to practice with the Honest John and fire off a rocket. No warhead, of course. And they launched a rocket just like this, but they forgot to detach the trailer. So the rocket flew up in the sky, and it dragged that wheeled contraption that you see there that's used to pull the rocket. And this trailer went flying off at enormous velocity into the West German countryside. On the right, you can see the Soviet-tracked Scuds. These are on all different kinds of platforms. So the Soviets have tailored the transporter, erector, launcher for different types of terrain, whether there were a lot of roads or what kind of terrain is there. Now this is the next type of platform, not platform, but vector in which you can launch a warhead. This is the ABM, the Antiballistic Missile. We're going to have a whole lecture on this system because it's got a lot of interesting philosophic perspectives to it, and it answers the question of why most countries don't have ballistic missile defenses, or why the systems they do have are quite thin. This here is a Soviet Galosh system, which was deployed around Moscow, and it's got a nuclear warhead. When I, again, visited Moscow in 1987, I immediately knew where all the locations were because I'd researched it beforehand. And on the pretext of visiting some churches, which is actually just about as bad an idea as looking for an ABM site, I went out looking for the ABM sites. And I didn't go more than half an hour before I was intercepted by someone sent out by our guide and brought back. So I've never successfully seen a Soviet or Russian anti-ballistic missile facility. So here we're going to examine the intercept measure. This equation indicates the number of warheads required to obtain a certain probability of destroying an incoming missile. And the specific formula is 1 over n is equal to 1 pk divided by pk, where n is the number of missiles required. So this is ultimately the dependent variable. It's the value we are trying to solve for. Now, IPK is the interceptor probability of kill. It's the individual ability of that interceptor to hit and destroy the target. PK is the desired probability of kill against an incoming target. Now, why would these not be the same thing? Because it's actually more cost effective and creates more certainty to have layered defense. So you'd launch a rocket, and it's cheaper to have a rocket that's got a 40% chance of intercept instead of an 80% chance of intercept. So you'd build cheaper rockets, and if you missed it in the first line of defense, then you'd fire a second rocket to intercept it at the second line of defense and the third line of defense. So it's a much more efficient way of defending against targets. So let's apply it to a problem. So here we have an interceptor with a probability of 60% and a desired kill probability of 80%. Okay, and this is just the first layer. You know, when it gets to the second layer, we could have a different kind of interceptor. For example, as we'll see later on, when the Americans had their ballistic missile defense system in the 1970s, they had two different kinds of interceptors for two different kinds of ranges and circumstances. So the way that we do the calculation, it would be 1 over n equals 0.6 divided by 0.8. We would, of course, do the division of the fraction, which is going to equal a certain value. And then we're going to end up with 1 over n is equal to that value. What you want to do is multiply both sides by n. All right, and what that's going to do is going to allow you to cancel the n on the left side and leave you a value of n on the right side, n times whatever value. And then you're going to divide both sides by the coefficient of n, which is going to be 1.33, which is 0.6 divided by 0.8. And so that's going to essentially move 1.33 to the other side. And you'll end up with 1.33 is equal to n. Or as you read it here, n is equal to 1.33. Now you automatically round up. All right, so you're going to round up, and that'll be 2 interceptors because you can't launch a third of an interceptor. So the answer is 2 interceptors are required for an 80% kill probability when you're using an interceptor with a probability of 60%. You probably knew this intuitively. If you want to get to 80%, 60% is not enough, just fire 2 rockets, okay? But for more complicated applications, the formula would be too big for you to be able to interpret it intuitively. The next type of vector for a nuclear warhead is the SAM, the surface-to-air missile. Now this here is the Nike Ajax system. These were deployed next to every major city in the US. They were deployed into the 1990s and the early 2000s in Italy and Turkey. These are enormous long-range missiles. They're meant to destroy high-flying, high-speed aircraft. And they can also destroy targets at the medium range, rather medium altitude, but very long range. So these were very efficient systems. There were also air-to-air missiles that were nuclear. On the top left, we have a genie. We can see the genie being launched from an airplane. And look at on the top right and the bottom right. Look at the symbol on those airplanes. Those are Canadian aircraft. The Canadian Air Force operated the MBO-1 nuclear Genie air-to-air missile. Now, why would we do that? Because Canada, as a part of NORAD, was responsible for intercepting Soviet bomber attacks over the Arctic Circle that would have flown through Canada and then dropped bombs or fired cruise missiles at Canadian and American targets. Now, American soldiers guarded the warehouse, typically a 19-year-old with a rifle, where the warheads were kept. But Canadians were fully trained and equipped to operate these missiles in a time of war. These are sea-launched cruise missiles. Now, cruise missiles are like the V-1 glide bombs that we saw earlier. They basically have engines that cause them to fly quite low and quite slowly. Most in fact have rocket engines, some have airplane engines. There are hypersonic versions that are being explored that move very, very quickly, but not a lot yet at the moment. And there's serious questions about them because they don't turn well, which means they can't fly very low because they're going to hit a tree, and that'll be the end of them. The thing about cruise missiles is because they fly low, they can be very accurate, as long as they're not jammed or somehow masked. Look-down radars, which modern aircraft were equipped with selectively in the 1980s, could already identify them and destroy them. But you can't possibly deploy enough aircraft permanently in an area to catch even a small fraction of the cruise missiles. Now, cruise missiles can be launched from a variety of different submarines. They don't have to be launched from a vertical launch system, a VLS. They can be launched horizontally through a torpedo tube. And these systems, being very accurate, they're useful against high-value targets. But like I told you in the previous lecture, missiles are always more expensive than an airplane. They have a very small payload. I mean, that cruise missile that is launching here has a much smaller explosive in its warhead than an aircraft. So these will be launched when you're afraid that aircraft would suffer too high attrition and pilots would be killed And so you accept that maybe 70% of these cruise missiles would be destroyed, but if you can destroy that one radar site, then it opens up an opportunity for the rest of the aircraft to barrel through and hit their targets. So you've got here a picture of a Soviet Echo 2 ballistic missile submarine on the top. In the center is a U.S. ballistic missile submarine, and the bottom is the open hatch of a U.S. ballistic missile submarine. The second way to deliver nuclear weapons is by bombers. So what we have in the top left is a B-2 stealth bomber, which is basically an elaboration of a system designed in the 50s, which is a copy of a German World War II experiment. Now, Plattsburgh Air Force Base, which is deployed just south of Montreal, in the 1980s was a source of KC-135 tankers, which is what you see here. This KC-135 tanker is refueling the B-2 bomber. And every day we'd look up into the sky because the B-52 bombers from the U.S. would deploy in the Arctic Circle and do basically runs against the Soviet Union, 24 hours a day, 365 days a year for decades. And they would be able to do that because they'd be refueled by these KC-135s. So you could look up in the sky, and these would be flying over Montreal all the time, all the way to the Arctic Circle. It was just an unbelievable spectacle. And you know, retrospectively, I think it was an incredibly aggressive act on the part of the U.S. to be constantly flying the B-52s against the Soviet border. Bottom left, we have, of course, a B-52, and it's equipped with SRAMs, short-range attack missiles, and these are potentially nuclear-equipped rockets. So the B-52 doesn't have to go into hostile space; you can just drop those rockets off. You can see on the top right a B-1 bomber. It started off as a penetration, high-speed, low-altitude bomber. But Soviet defenses got so good by the end of the 1970s, the program was canceled, and they had just a few bombers that were built, which at the time was approximately 100. And these bombers were meant to go up to the frontier of the Soviets and then drop their payload. Today they're used for conventional bombing. I've met a pilot who, not only a pilot, but a squadron commander of the B-1s, and they love their airplanes. Underneath that, we have the Tupolev 22 blinder Ms, rather not the Ms, not the M version, sorry, just the flat Tupolev 22 blinder. These are Soviet-era bombers. Occasionally they sold them to other countries. The Soviets sold one to Libya, which I think was done for cash, because the Libyans had oil exports that went to Italy, and the Russians needed hard capital, so they obviously traded for lira. The Libyans, I think they used it once in an Arab-Israeli war, or they bombed Egypt with it or something. I'm sure not put to good use. And the final bottom right aircraft is the Mirage 4, which was the French aerial deterrent, which was supposed to carry an ASMP nuclear bomb to Moscow. And there was always the question of the problem that the French Mirage 4 had enough range to get to Moscow, but not enough range to get back to France. So where was it going to go after that? So this is a nuclear bomb broken up into its components. It's a B-83 1 megaton bomb that can be dropped by a B-2 or a B-52 bomber. So you see all the different components to it, including what looks like a parachute. So that's sort of an interesting thing to study. Perhaps you could guess what the different parts do. Then there are air-launched cruise missiles. And you can see the top right, a standard model. During the Cold War, the Americans would test their cruise missiles in Canada's Arctic, because we had the space. And there's a lot of political discourse about that, particularly from the left. They would go out and demonstrate and stick up signs hoping to catch the cruise missile, which I thought was inadvisable. But Canada was doing its part for Western defense. You can see a B-52, which is there dropping a very large SRAM, a short-range attack missile. No, actually, it's not a SRAM. I'm sorry. The SRAM is on the bottom right. And there you've got a rotary magazine that drops these off. What we have on the bottom left is a Hound Dog, which I believe is a 1970s era cruise missile. Again, nuclear capable and rather large. Now, what we have in the top right is the aircraft we identified before, the Tupolev 95 Bear, that today flies off the coast of Canada's Arctic. Here it's carrying something called a Kangaroo AS-3. This bus-sized rocket flies at multiple times the speed of sound, and it was designed with a nuclear warhead to blow up U.S. aircraft carriers. So you can imagine the U.S. Air Force spent a lot of time focusing on trying to intercept these bombers and intercept these missiles. And that was the design. The Americans designed the F-14 Tomcat interceptor, which launched off carrier decks. And those aircraft carried the Phoenix missile, which was a very high-speed, very accurate, most expensive air-to-air missile the Americans built. And I think perhaps even in its non-nuclear component, certainly more expensive than the Genie. So this was a major threat. So this is a sort of a tactical naval application. But you could use a Kangaroo just as easily against a port facility or a coastal airbase. Then there's artillery. We talked before that the optimal design of a nuclear artillery shell would be a gun design, because the amount of stress on a shell that's chemically propelled would cause the internal components of an implosion device to disintegrate. So what we have at the bottom is a U.S. nuclear-capable M110 self-propelled artillery piece. And what we have at the top is rather peculiar. These are, of course, frogs, free rocket over grounds, designed by the Soviets. But if you look at the flag on the side of the vehicle and the rockets, it's East German. So what the heck are the East Germans doing with missiles that have nuclear-capable warheads? Well, it's thought, in fact, that since 4% of the warheads that the Soviets had stored for the rockets were in East Germany, were chemical warheads, that East Germany was permitted to train for the use of chemical weapons on the battlefield. And so these would have been nerve gas. And the nerve gas would have been dropped on an airfield. And nerve gas is problematic because, of course, it disturbs your nervous system. But for a pilot, it gives you severe double vision and massive headaches. So try landing an airplane, or try conducting very difficult bombing maneuvers at high speed when you have double vision and you have a massive migraine. And that's if you live. Of course, there are torpedoes with nuclear warheads. You've got torpedoes that are launched from submarines with nuclear warheads. There are, of course, ships that fire torpedoes at submarines, torpedoes like the Mark 46. There are, of course, helicopters which drop torpedoes once their sonobuoy or their floating microphone has detected a submarine. And these torpedoes are smart. They'll go down and they'll search for a wake. They'll search for some differences in the water. Some of them have active sonar, and so they'll chase down an object and then detonate a nuclear weapon nearby. You've also got aircraft that can drop a nuclear torpedo, like the P-3 or the P-8 or the British Nimrod or the Ilyushin 38 Mainstay, which is the Soviet-era maritime patrol aircraft. Here you can see a Soviet Hotel 2, which is not quite a... It's a sort of a ballistic missile submarine. It's equipped with the SSN-5 Serb, which is, I think, a vertically launched rocket, but I don't think it's definitely not a ICBM. And on the lower left, you've got the U.S. Polaris firing a sea-launched ballistic missile. Of course, you have helicopters that can drop nuclear depth charges. Now, the Canadian frigates built during the Cold War are not equipped with nuclear depth charges, but they can operate them. Because I spoke with some of the sailors, and they showed me the ops center in the frigates, and I could see that they had options to be able to do that. So in this picture here, you've got the British Her Majesty's Ship Resolution ballistic missile submarine, and with a Sea King helicopter. And that Sea King helicopter, in its anti-submarine warfare configuration, can listen to, find, and then drop a nuclear depth charge on top of a submarine. I was an Army engineer, and we did a lot of demolitions, and we did demolitions occasionally underwater in order to practice blowing up the piers of a bridge. So I'd ask you, when you do a detonation, does it move faster or slower in a heavier medium? So if you detonate underwater, is the water going to stop the explosion, or for some peculiar reason is it going to accelerate it? Well, in fact, when you detonate anything in water, it accelerates it. The heavier and denser the medium, the more powerfully it transmits the shockwave. So we were always warned severely, if you put an explosive in the water, get away from it, because that shockwave is going to rip you apart. This is a tragic story. A year before I went on my military training in Chilliwack, there was an officer's course there, and they were using a camouflage tube, which is a tube that you bang into the ground in order to create a cratering charge. Because one of the roles the engineers have is to destroy roads so that Soviet tanks are slowed down, and then they have to use their engineer assets to fix the road, and while they're doing that, you can bring artillery on top of them. So we had some officers that were training that were banging a tube into the ground, and then once you've done that, you push down into the tube trigrand, which looks like nerds, but it's a type of explosive that's activated when you pour water down the tube. It's rather bizarre. And then you take C4, and you have a sort of a booster charge, and you have det cord around it, and you wrap it around, and then you push it down the tube. And a horrible accident occurred. Someone had used a ferrous artillery rod to push the explosive down the tube, and the problem with ferrous material is that it sparks. In the engineers, we have knives, for example, that are made of metal, partially nickel, that don't spark, because we work with explosives all the time, and we cut explosives. And it set off a spark, and a huge explosion occurred. The individuals immediately above the detonation were thrown into the air and were injured and fell down some distance from the detonation. The people that were farther out, 3 or 4 meters, were standing on the ground, and the shockwave somehow got out to where they were standing, and they were obliterated and blown to pieces. And I just can't imagine what psychological scar it would have left on me if I was the one there. But I knew people that were there, and who else has to do this? They had to pick up the body parts after this, and it caused a significant revision of the safety standards for the training with camouflage sets. And it was found that, or rather suspected that it was the artillery rod that was ferrous that was somehow borrowed and inappropriately put into that situation. So a nuclear depth charge detonated underwater is going to destroy submarines for a very great distance, because the thick medium of water is going to carry that enormous shock wave a huge distance. So you really have to hide. If someone even has a remote idea of where you are as a submarine, you're dead in a modern anti-submarine warfare situation. Finally, as an Army engineer, this is something that we would have been probably tasked to do. This is an ADM, an atomic demolition munition. It's a backpack nuke, typically deployed by special forces to destroy key infrastructure like deep tunnels, perhaps the St. Bernard's Pass tunnel going through Switzerland, or the tunnel connecting Kabul to Pakistan, or the Norwegian highways along the coast, or mountains going through the passes of the Zagros Mountains in Iran, perhaps a Soviet column trying to get to the oil-rich Persian Gulf. So most of these systems have been discontinued since the end of the Cold War, but they did have a very useful role, and there were a variety of different systems. There's always been paranoia that Soviet or fifth columnist socialist elements, fellow travelers, would bring nuclear bombs in briefcases into the U.S. and detonate it, and then the U.S. wouldn't be able to respond. It's a concern that's been around since, well, the 1940s. I guess there's no real response, except that if you get nuked, you can always assume that your worst enemy probably had something to do with it, and you just fire back. So it does give an incentive to everyone involved not to have people walking around with nuclear briefcases. So let's look now at the calculations for first strike survivability. What we want to do here is make a calculation for what's the chance of a rocket destroying a target. So we're going to have a rocket launch from the other side. It's going to fly over and hit our side's missile. And then it's going to detonate. And then our missile is going to launch. Now we want to calculate all the different components of that launch sequence to see whether our missile is going to survive and launch. Now the data for these equations and these variables comes from your reader, okay? And the page number of the text it comes from, most of it is from James Dunnigan, who is the author of How to Make War, Columbia University grad, and has just an incredible grasp of military history and strategy. use the page numbers not of the reader, use the page numbers of his actual book. Okay? So this is a problem that happens every year. The students go, the page numbers are not there. I'm telling you right now, they are there. You simply have to ignore the reader, get to the correct reading by James F. Dunnigan, and then look at his page numbers. Okay? We're using the original page numbers because you might find his book online in PDF form somewhere and use that version. Okay, so here are the different variables. PS is the probability of launching a missile, surviving a first strike, and launching. So this is your missile. Okay. The probability, PK, is the probability of the attacking warhead destroying your silo. And you can see it's a lot more, the second formula is a lot more complicated. Now again, what you're going to see as the emergent property of the formula is that missile accuracy is so much more important than megatonnage. LR, which is one of the variables in that second equation, is the maximum distance at which a warhead will destroy a silo. All right, and it's approximately 470, which is a constant, times Y divided by H. Y is the yield of the weapon, H is the hardness of the silo. So here are the other variables. You have R1 and R2, which is the reliability of targeted and incoming missiles, respectively. This is an issue. If you built a missile, how well is it going to work when you finally deploy it? A1 and A2 are the alert status. Believe it or not, most weapons are under frequent maintenance. They're always breaking. I had a guest speaker in my class who privately told me that he dropped the hammer down the silo and banged it on the side of the missile. And this is a big no-no because there was an incident in the 1980s where that occurred and it actually set off an explosion of the propellant. And it was a big disaster. You'll find the story on YouTube. And it was at the time basically exposed the incompetence of the military's higher command at dealing with that kind of contingency. Although the individual soldiers on the site did their best to deal with the problem. Because of course you had a rocket that exploded and the warhead was ejected and thrown onto a local farmer's field. And you know, people running all over the place worried about radiation. Y is the nuclear yield in kilotons. H is the hardness in PSI and ranges between 100 and 3,000 PSI. And of course you know what CEP is. It's the circular error probability. What you also see here, of course, is a missile being lowered into a submarine's vertical launch system. If you look at the top, you're going to look at some of the estimates of the PSIs for different silos built in the Soviet Union. You can see they range from 28 PSI, which is very early preliminary use of cement and reinforced concrete. Below is images of suffering. I mean, obviously you've got someone on the left with scar tissue surviving being hit by a nuclear weapon. You've got melted glass, and on the bottom right you have a typical burn victim immediately after being hit by the thermal damage of a nuclear weapon. And this is war, right? War is inflicting pain, and you don't kill everyone. There are a great many injuries. So here is our example. I'm going to have to perhaps take a break in parts of this because we want to show you how to actually do the calculation using a calculator. So the particular example we have here is we have an incoming missile. We haven't identified the type, but we go by type in your assignment. The missile has a 90% alert status and a 90% reliability. And it's a warhead of 300 kilotons. And it's got a circular error probability of 200 meters, which is fantastic. And it's inbound on a silo that's got 2,000 PSI, and inside is a missile with 90% alert and reliability. So the first thing we want to do is calculate LR. The LR is basically the calculation of, can we get the fireball and the PSI shockwave on top of the silo? Okay, so we know the constant's 470. We insert the warhead in kilotons, which is 300. It's divided by the PSI of the silo, which is 2,000, and we do it to the exponent of 1/3. So do the 300 divided by the 2,000 first. Get the exponent of that, which is the cube root, and you can find it on your calculator. It'll typically be the to the power of the exponent of 3, but there's an inverse function or a shift function that then converts it to the cube root of 3. and that's going to give you a range of 250 meters. So you've got to get that warhead to within 250 meters of the silo. So then you're going to go on and calculate the PK. Now here we have alert times reliability. This is fairly obvious. It means that the missile's available 90% of the time. 10% of the time it's under maintenance, and 10% of the time it's not going to work. It's going to fly off somewhere else. And here we multiply that by 1 minus 2 times, and then we have to calculate the exponent. Okay, and in the notes I've actually given instructions on how to do that calculation. And for a conventional calculator, it's going to be 2, and you're going to see an X superscript Y symbol somewhere on the calculator. It basically means X to the power of Y, and you would insert your number, whatever that result is going to be. And I can tell you, I can actually tell you what the value is going to be. 250 divided by 200 is going to be 1.25. So you have 1.25, and you got to make that a negative value, right? So what you're going to do is press plus or minus. There's a plus/minus key on the calculator. It's going to give that a negative value, and then you're going to press the button, right? So you're going to have 2 X superscript Y, where Y is equal to 1.25. You make that a negative. You hit the button, and it's going to give you 0.42. And then you can carry on with the calculation. It's going to be 1 minus 0.42. You square that. So it'll be 0.9 times 0.9 times the result of that, and that'll give you a PK of 0.2724. Okay? So the next step is you have to figure out whether your own missile is going to work. Is it ready? Is it reliable? 0.9 times 0.9 times the 100% chance it's going to live minus the chance it's going to die because the other bomb is going to go off nearby. So it's going to be 1 minus 0.2724. So the PSI, it does give a lot of protection. It's only a 27% chance of this missile being destroyed, even with a missile with an incredible circular error probability of 200 meters. And the final value is 0.589. So there's a 59% chance that the missile in the silo will survive the first strike and ultimately launch. So, big question. Well, again, we have a picture here of this time a different aircraft. This is a Tupolev 16 Badger, which is an aircraft from the 1950s. It later led on to the Tupolev 22 Blinder, which is the other Soviet aircraft that you saw. And it was ultimately built into the Tupolev 22M, which I have not yet shown you. It's called a Backfire, and it was the scariest aircraft in the Soviet arsenal for 20 years. And it's still a formidable aircraft. This aircraft here is still in use for electronic warfare and surveillance purposes. The Chinese use this system as their frontline bomber, although they're trying to replace it with a stealth wing aircraft like the B-2. Here we have an AS-1 Kennel. It's a cruise missile. It's got an air intake at the front. It's nuclear, and it can also be used against aircraft and coastal facilities like airfields and ports. So this is an earlier version of that nuclear anti-carrier system. So we have a question. Do we have enough warheads? The U.S. built 73,000 nuclear warheads of all types between 1945 and 1994. That's a lot of warheads. But there was always a question of, well, what's going to happen to these? How many are we ultimately going to need? It would be very, very strategically incompetent if you were fighting a nuclear war and then you ran out of nuclear weapons. That would be a severe problem. So let's start with some factors that could reduce the number of warheads you would have. So let's say you started with a total number of 1,000 warheads. Maybe 80% are serviceable at any one time. I mean, if you wake up in the morning and say, launch now, you're going to find a lot of your nuclear weapons won't be ready to launch. So maybe 80% are serviceable, and I think that's a very realistic value. Say that 75% are reliable. I'm not saying that they're going to fall apart in the midair, but I'm going to say they're going to miss. They're going to miss because the telemetry system doesn't work, a gyro gets whacked out, or there's a weird weather event, or you're flying it through a tornado, or a hurricane, or a heavy rainstorm, and it's going to go off to a different direction. And technology, it always works much worse than you think. You know, World War I, everyone thought, okay, well, I need one cannon to fire one shell to kill one soldier. So, you know what, after 3 months, I've calculated, I've wiped out half the German army, or half the British or French army. It didn't work like that. It took hundreds of shells to kill people in World War II, in World War I, because people were dug in the ground, and the war dragged on forever. I would not be surprised if nuclear weapons on the battlefield were much less effective than we estimate now, because of the ability of humans to disperse and the ability of humans to deceive and to hide. And that's not a completely crazy idea. If you think about it, during the Roman era, you'd put 20, 30,000 soldiers packed shoulder to shoulder on a battlefield, everyone there. And you would fight a huge battle. The battle would last several hours, like a rugby match, and people would stab each other. And maybe a third, maybe half of the losers would be killed. That's like a 50% death rate. But with machine guns and artillery in the 20th century and the late 19th century, people dispersed. The modern battlefield, you can't see anyone. In World War II, those same 15,000 soldiers that would have been packed together like sardines in a valley in the Roman era were spread out over 20, 30, 40 kilometers. If you walk into a town defended by a division of soldiers, you would see nothing. So today, soldiers have an incredible ability to disperse, and the main reason is leadership. Soldiers are much more confident. They know why they're there. They're given a map. They're given a mission, and they don't need to have someone supervising them immediately like the farmers that served in the Roman army. So maybe soldiers will disperse so much that nuclear weapons will be far less efficient. The next is surviving a fratricide, right? Missiles that enter another's lethal radius is going to lead to a lot of warheads destroyed. Here I'm positing 1/4 of warheads are going to get destroyed in fratricide. Right? It could be as high as 50%. Depending on how you pace out the incoming missiles. Now, 30% of missiles that you don't launch will be destroyed by enemy action. I had a teaching assistant over a decade ago who was a colonel in the GRU, Soviet Military Intelligence. His job was to train allies, militant allies of the Soviet Union in the developing world. He trained the Vietnamese, who he thought were the best soldiers he ever trained. He trained a lot of groups from the Middle East, including competing factions in Lebanon. Now, the one thing he did tell me was Patrice Lumumba University is not, in fact, a training ground run by the KGB or the GRU. Now, before he had that role, he was in a recon element of a Soviet motor rifle division in Czechoslovakia, and their mission in the event of a Third World War, meaning an invasion of West Germany, would have been to drive along the Danube and then to cross over through the Italian Alps and drive into northern Italy and to hit the Po Valley. But his tactical mission was to hunt and kill NATO nuclear weapons. So he was going to be out in front, operating in light vehicles and helicopters, chasing down wherever they thought NATO missiles were. And, NATO's got all these missiles everywhere. If you're not firing them, you're hiding them. And a lot of them are going to get destroyed and caught. And destroying nuclear weapons depots and mobile nuclear weapons platforms was a priority for everyone all the time. So only 30% of them destroyed? That might be an underestimate. It could be as high as 50%. Now, decoys. Half of all nuclear weapons are tactical, half are for strategic purposes. So you're firing a lot of nuclear weapons against ports and submarines. During the Falklands War, the British fired hundreds of depth charges against Argentinian submarines. There were 5 Argentinian submarines. None of them were damaged by depth charges. The ones that were damaged were hit by anti-ship missiles because the submarine came up for air and they were hit in the side. So imagine if you're desperate to preserve your aircraft carrier, you're going to be firing probably several hundred nuclear depth charges, and they're going to hit nothing. You're going to kill a lot of fish. So decoys, in which you try to get the other person to fire nuclear weapons at you to waste their nuclear weapons, could be anywhere from 0% to 90%. So what does that leave us with? 1,000 nuclear missile warheads, it's only going to have the effect of 350 warheads, or as low as 10. Right? And how long are 1,000 warheads going to last? A week? 5 days? 48 hours? There's also the problem with delivery, right? You're going to have to preserve a reserve of weapons, and you're going to see this later in the simulations. If you want to negotiate politically, it's not about what you destroy. It's about when the battle is done, are you still able to threaten the enemy? So you're going to have a reserve of nuclear weapons so that you can approach your adversary and say, listen, I've won. And the proof that I've won is, if you don't stop, I'm going to nuke you all over again. So you need to reserve a large portion of your nuclear weapons to engage in the political negotiation that occurs at the end of every war. Now, Karl von Clausewitz called war is politics by other means. He was a Prussian officer who wrote a book called On War, Der Krieg, and he wanted to figure out the difference between war and theory, where two sides fight each other to the death and endlessly, versus real war. And the answer is real war is guided by politics, because war is very expensive and inflicts a lot of pain. And people don't want to risk their life for war, so unless it's for a good purpose. And so people are very reluctant to allow their leaders to go to war. So when you do go to war, it has to be for a good reason. And as soon as you've achieved that reason, you end the war, which is why the vast majority of wars are short, and war, in fact, is very rare. It's always happening somewhere, but it doesn't happen for an individual country for a very long time. So if war is politics by other means, you need the instrument to continue the politics, and that would involve the threat of continuing to use nuclear weapons. However, nuclear weapons have an enormous amount of diminishing returns. By the early 1960s, the US had enough nuclear weapons to destroy every major Soviet city. The American Defense Secretary, Robert McNamara, argued that increasing the US arsenal from the few thousand warheads they had to the many tens of thousands that the Pentagon wanted would only, and if the US had increased those missiles and had used them all, they would have only increased the additional damage to the Soviet Union by 30%, because there were no more targets. Once you blow up the top 10 cities, then you're hitting the bottom 30 cities, and then you're going after towns, and then you're going after villages and crossroads and lone buildings and fields. You run out of targets very quickly. This is an Egyptian Tupolev 16 Badger, the same aircraft I showed you earlier, equipped with AS-5 Kelt rockets. The Egyptian rockets, of course, were non-nuclear. Now, this is a chart that comes out of the text. In fact, it's exactly the page where you can get some of the values for some of the assignments. This is from the Dunnigan text. Now, you've got missiles listed in sort of the vertical left side of the page. A number of missiles deployed, the number of warheads they have, total warheads, equivalent megatonnage, which I've already shown you to calculate. And then there's the K. What is the K? The K was a calculation that Dunnigan derived. It was a current problem that people were dealing with in the 80s, showing that American missiles had become so accurate they could overcome and destroy most of the Soviet missiles in their silos. And this was very problematic because it made the Soviets feel insecure. So it's one of the reasons why the Soviets began to deploy their missiles onto mobile systems, to get them at least moving out there. And we're going to look later on, when we look at command and control and other aspects, we're going to look at how vulnerable Soviet and Russian mobile systems are in comparison to conventional technology. Now, maybe it would have been better just to leave the missiles in the silo. So the Americans, here the calculation is, by the early 1990s, the Americans had 335,000 K attack factors, and that was broken down between 124,450 land K defense and 579,000 CK defense. Whereas the Soviets had 11,164 K attack, which gave them 240,900 land K attack defense and 280,000 CK defense. And it basically boiled down to the Soviets were vulnerable. The Americans had emerging vulnerability, but the Soviets had serious vulnerability. The K factor is basically the equivalent megatonnage divided by the circular error probability, and it worked its way into the counter-military potential assessments. So U.S. accuracy gave the U.S. a far more powerful force for counter-force attacks than the USSR possessed. The U.S. had enough power to destroy the Soviet land-based missiles in a first strike if the Americans could manage a first strike. but insufficient for both land and sea. So the Americans couldn't destroy all the Soviet submarines and at the same time destroy all the missiles in the silos. If the U.S. went after the ballistic missile submarines, which was advocated by Canadian Colin Gray, who was hired to work at the Pentagon as a nuclear targeter, and we're going to talk about him later because he has some interesting ideas about strategy, then the Soviet nuclear force would have been very severely weakened. In contrast, the Soviets, even by the late 1980s, didn't have a critical mass of accuracy to be able to overcome and destroy the U.S. missiles in their silos because of the poor accuracy of their arsenals. And the Soviet naval arsenal was very inaccurate and couldn't even strike U.S. missiles in their silos.